Hello. In this video, I'm going to cover the lid-driven cavity flow tutorial, which is our first tutorial in OpenFOAM, and I'm going to be using OpenFOAM v2412 for this. So just to introduce the problem definition itself, we have a cavity, which is essentially just a square. And on the left, right, and bottom of the square, they're just physical walls. So that just means the velocity is zero, there's no slip. And at the top, we're prescribing a velocity of 1 meter per second in the from left to right. So conceptually, how you can imagine this being applied is maybe like a conveyor belt is like moving along the top of the fluid, pushing it to the right. So this is a standard test case in CFD, and this is the first one we're going to look at in OpenFOAM. So the governing equations in this case, we have just the Navier-Stokes equations, and they're expressed in their incompressible form for a Newtonian fluid. So conservation of mass, which becomes conservation of volume, and we have mass by acceleration and our viscous forces and pressure forces. So the unknowns here are vector velocity and scalar pressure P. So we've divided across by density here, but actually OpenFOAM just brings this density in to the P, and it just defines something known as kinematic pressure. So P divided by rho is kinematic pressure, and that's what OpenFOAM is actually solving for. Let me jump across to my terminal, to my Windows. Okay, so I will search for Ubuntu. So I'm assuming you've already installed Ubuntu and OpenFOAM, and you can check previous videos to see how that's done. So I'll just make this larger by double clicking on it. And just in the bottom corner here, you're going to see that the keys that I'm typing will appear just to make things a little bit easier in case you're struggling to follow what I'm doing. You can, if you want, you can make your font larger. You can go to settings here. And if you go, there's lots of settings you can set. But if you go to defaults, you can set your font size here as well. So if I go back over here. Okay, so the first thing we're going to do is we're going to load OpenFOAM 2412. So there's a number of variants of OpenFOAM. So there's openfoam.com and .org, and they have different numbering conventions. So the cases themselves are very, very similar, but some of the commands are slightly different. So if I type OpenFOAM 2412, this will load OpenFOAM 2412 in this for this version. So the first thing I'm going to do the very first time I load OpenFOAM is, if I haven't done it already, I'm going to make what's known as the run directory. So the run directory is where we're going to store models. And it's just a convention. You can put your models anywhere. But normally in OpenFOAM convention is we just keep them in this folder called a run directory. So to create that run directory, you'll type make dir, and OpenFOAM will already define a number of what are known as environment variables. So I'm writing the $ and then capital foam underscore run here. And then I'm going to type -p. So what this is doing here, this thing is called environment variable, which is essentially the environment variable is foam run, and $ just means use the value of it. So there's many of these defined by OpenFOAM, and this is just a shortcut for just an address. So I can actually use a command called echo to see the value of environment variable. So if I go foam run like that, you can see that all it's doing is when I go $foam run, it's just giving this address, this working directory. So there's a variety of other ones as well. So if I go $foam like that and I press tab twice, you'll see that there's lots of other ones defined as well. So we're going to use foam tutorials later as well. Okay, so then if I change directory to my foam run, I can go like that, cd foam run, and print working directory. That brings me to there. But OpenFOAM actually defines a shortcut, which is just run. So that's called an alias. So if you just type run after loading OpenFOAM, it's just a shortcut for cd run. Just to comment back here, I use a -p. So -p just means parent. So it's create that run directory, but if any of the parent directories don't exist, then create those as well. So for example, in this case, this Philip CV2412, which are my user files in OpenFOAM convention for 2412. If that didn't exist, it will make that as well. Okay, so we can go to the run directory by typing run. See we're there. If I type cd and enter, it just brings me back to my home directory. Let me just hold down enter a little bit, and then we can see where we are, and then I can type run again to bring me back to where I am. So let me just drag this thing over here because it's in the way. Okay, so if I go to the run directory, and this is where I am at the moment. Okay, so the it can be useful as well if you're using Windows WSL, if you type explorer .exe dot, that will open it up in just in Windows Explorer so you can see a case and where it exists. Or you can see where we are in the same folder. So you can see I already have this cavity folder, but I'm going to remove that and we're going to do it again. So I type ls, you can see the cavity folder there. Okay, so OpenFOAM comes with a bunch of cases already prepared and made, and they're called tutorials. So we're just going to find the cavity tutorial and we're going to copy it and then run it or make changes to it. So we already saw that we could type cd $foam underscore tutorials. And you'll see I'm making use of tab a lot. So tab is autocomplete. So it's probably the button you'll press the most on the terminal. So if I go to the tutorials and I type ls, you can see they're broken down by various application areas. So we're mostly going to be focused on incompressible flow, which is here. But there are some other ones as well that you might be curious to, and you can go in and examine them. So if I go into incompressible, um, they then break them down by solver. So in Fluent, you just press go and it will run depending on the settings, different code in the background. But in OpenFOAM, or at least in this variant of OpenFOAM, they will have separate solvers. So for example, icofoam is what we're going to use here. And icofoam solves the incompressible laminar Navier-Stokes equations that we just looked at. Um, but there are other solvers as well, and we'll go on to look at some of those on different ways to solve things. So if I cd into icofoam and I ls, it has a couple of cases. One's called cavity. There's some other ones here as well. I'll go inside cavity, and there's actually a couple of versions of cavity. So there's another one here called cavity inside that. So I'm going to copy this to my run directory. So I could run it and change it here, but the problem is it will, if I break something, then I'm messing up my installation. But actually, this is in a system location, so I probably can't actually change these files anyway. So if I type run, go back to run, I'll go cp-r, home, tutorials tab, and press tab as well, so it'll show us our options. If you want, when you're typing, sometimes there's problems in terminals where it'll put a backslash at the front when you go tab. So if you go escape and then let go and then press Control E, it will auto-complete the environment variable. Sometimes that can fix issues that people are having. Incompressible, icofoam, and I'm using tab a lot here, cavity, / cavity. So that's the case I want to copy. And I'm already in the run directory. I just want to copy it to here. So dot means here. And so if I ls now, you can see now I have a cavity case. So I'll cd in here, and here's my cavity case. So I will open it up in Explorer as well, just so you can have a look. So OpenFOAM cases, unlike other softwares, normally input files in other softwares like Fluent and Abacus are just a file, and the file describes the mesh and the boundary conditions and other numerical settings. But in OpenFOAM, the input files are defined as what's known as a case, and cavity here is the case, and a case is just a directory or a folder. And inside that folder directory, the input files are split into subdirectories. So OpenFOAM cases will always have these three folders or similar folders. They'll have a 0 folder, a constant, and a system. So 0, if I click in, it has a P and a U. So this represents the pressure or the kinematic pressure and the velocity file. So this is where we're going to put our boundary conditions and we're going to put our initial conditions. The constant folder, which we're going to as well, is where we're going to have things like material properties, and then the mesh will be put there as well. And then system folder are various things to do with setting the time steps and the discretization schemes, and sometimes, depending on the mesher we're using, defining the mesh inputs as well. So I'll have a quick look here in the case. So I'm going to use Emacs, but you can use other text editors. So if I go Emacs / U, that will open up Emacs. And if I don't have Emacs, I can just install it. So in Ubuntu, you can go sudo apt install softwares if they're there. So let me just, I'll pause recording while I'm doing that. Okay, so that took a minute or two. So now Emacs is installed. So I can press up to look at my previous commands. So I can go back to Emacs 0u. And this opens the velocity file, the 0u file in Emacs. So all of these OpenFOAM files will have this header and then this foam file header information. But the thing we're mostly interested in is this. So it's saying the field has these dimensions. So in OpenFOAM, 7 numbers are used to represent dimensions. So all SI units can be given in terms of what are known as SI base units. So essentially it's kilograms to the power of this number, meters, second, and then Kelvin, and then there's other ones that are rarely used. So you can see this is meters to the power of 1, seconds to the power of -1. So meters per second is velocity. Internal field, this represents the starting values everywhere. So uniform is just basically a 0, 0, 0 velocity everywhere, but you can use other methods and utilities to prescribe initial values. And then these are our boundary conditions. So the top wall is called moving wall, and it has a fixed value of velocity in the x direction of 1 meter per second. And then the fixed walls are the left, right, and bottom, and they're set to no slip. So no slip is the same as just setting fixed value uniform 0, 0, 0. It's just a shorthand. And then as we'll see, OpenFOAM for 2D cases, it treats them as a special case of 3D where there's one cell in the third direction. So all models are 3D, and then it uses special boundary conditions called empty, which basically tell the solver not to solve in that direction. So I can, within Emacs, I can close Emacs with holding control, then press X. See? But actually, I can also, if I want to open another file, I can hold control and press XF. And then down here, it'll let me, say, type in another file I want to open. So a P in this case, press enter. So this is the P file. So I can see pressure is normally in pascals, but this is kinematic pressure. So it will be pascals per density. So Pascal is not a base SI base unit. So the SI base units for Pascal will be kilograms per meter per second squared. And then if you divide that by density, kilograms per meter cubed, then you'll end up with this meter squared per second squared, which represents kinematic pressure. So to scalar, initially the value is 0 everywhere, and then you can see these 0 gradient conditions for the walls, which is normally a standard condition for pressure near a wall. So essentially just means that the value of pressure right at the wall itself is just equal to the value that's just inside the flow domain, or like the closest cell center, essentially. This is similar to what Fluent will do. So I'll close out of this, Control X, C. If I go inside the constant directory, we have this transport properties, so I can open up that as well. So this is just the viscosity. Mu represents the viscosity, mu with M for mother, but nu with an N, that is the kinematic viscosity. So in the original equations for an incandescent flow, we normally specify the kinematic viscosity. So that's the real viscosity divided by density in this case. And then if we go back out, so up one folder into the parent folder, we're here, and then go back in the system. So we have a few files here. So we'll look at some of the important ones. So control dict, this is where we'll specify the end time. So start time is 0, end time is 0.5 seconds, and we're going to do delta t's, which are time increments of 5 milliseconds. And then the results are going to be written every 20 time steps. So these settings, you can control the time steps and how often the results are written. And there's some other settings here as well. I can also look at FE solution. This is to do with the tolerances of the actual equations that are being solved. If I go down here, I had some settings to do with piezo. We're going to leave those for now. And then I can look at something called FE schemes. And you have the discretization schemes that are used for the final volume method. So these settings you'll see if you've used Fluent and ANSYS, you'll see that the various tabs for the solution methods and the solution controls are very similar to what you see here. All right, so there's a few other files I'm going to ignore for now, except for one called block mesh dict. So in this case, we're going to make the mesh for this case using a mesher called block mesh, which is built into OpenFOAM. So block mesh lets you mesh geometry that can be described in terms of essentially kind of simple blocks or simple geometric shapes. So to run the block mesh measure, it needs to have this block mesh dict file, dict meaning a dictionary. So the geometry is defined in this, and we're going to have future tutorials are going to describe how this is set up. But for this case, it's basically already set up, and the key thing is it's specifying 20 by 20 cells in the X and Y direction. So if we go back to the parent directory of the case, the main case directory, where you can see 0 constant and system, if I run block mesh, that will read that block mesh dict file, and then it will generate the mesh. So if I look at this in PowerView now, I can see the mesh that's been generated. So to do that, PowerView is used to picking up results files as actual files, but in OpenFOAM, the case structure is maybe non-conventional. So to allow OpenFOAM or PowerView to open it, we normally create an empty file called anything.foam. So I'm just going to say case.foam. And if I use the touch command, so the touch command will just create an empty file. So if I ls now, I'll see just an empty file. If I open up with Emacs case.foam, it's just an empty file. And when PowerView finds a .foam empty file, it will assume that's inside a case, and then it knows how to read the OpenFOAM case around that. So that's what we're going to do. So if I go explorer.exe, this brings me to here. So I'll have this case.foam. So I've already opened PowerView on my computer, but the very first time you open PowerView, so if you just install PowerView from the PowerView website for free, and then you open PowerView, the very first time you open PowerView, you might have to associate PowerView with .foam files. And once you have, then you can just double click on these files. So I'll just wait for PowerView to open, and then I will show you how to do this. So this is PowerView here. The very first time it opens up, it has this examples guide. You can click on those and you can click in, they give you even visualizations to play with. But I don't want to see this anymore, so I'm going to just tick this box so it doesn't show it anymore. So I can actually just drag the case into here, and that's one way to load it. But you can actually affiliate it. So if you go right and show more options, and then open or open with, and then if you find the PowerView program, you go open with, you go to your C, program files, PowerView, and then there will be a folder called bin, which stands for binaries. And inside the bin, there will just be a executable called PowerView. If you click on that and then just say always open these files with that, and it will open it as well. So then you can just double click or click open, and it will open PowerView for you. So you can see I have a second version of PowerView here. So once you open it, if I just double click, make it full screen, the first thing to do is always press apply. So it actually loads the case. So this is the little reader, and it has some various settings that you might be interested in looking at. But here's my visualization of the screen itself. So if I hold on left click and I drag, that's just for rotating around. That right click is for zooming in and out. And then if you do have a middle click, you can use that to pan as well. So there's a couple of things here. At the top, this is for coloring, setting the color of this in various different ways. And then this is the representation. So I can go surface with edges to see the mesh. Or for example, I can go wireframe or points, or there's lots of other settings here like feature edges, etc. So mostly surface and surface edges is what I'm interested in. So this is the mesh. You can see it's 20 by 20. This is where the non-zero velocity condition is going to be applied. Okay, so I'm going to jump back to, let me see, I have two of these open. I can probably close one, but let me jump back to my terminal, my Ubuntu terminal. Okay, so the next thing I'm going to do is run the solver. So in this case, this case is set up for a solver called icofoam. So to run the solver, you just type icofoam and press enter. And then that's it. It takes a fraction of a second to run this case. It's very, very quick. So if I just scroll up and see what it's doing, you can see time is printed out. So you can see it's marching forward in time. It started at 0. If I scroll to the very top, eventually you can see it has this header all open things to print out the header and the version. Then it'll say it's reading the P and U files and transport properties, and it's using this piezoalgorithm inside icofoam. But effectively what it's doing is it goes to the first time step. It solves this piezoalgorithm will solve the momentum equation for velocity, and then it'll solve a what's called a pressure equation, which is a kind of modified form of the continuity equation. And it'll print out some residuals, and then it goes to the next step. So the piezoalgorithm, the way it's set up, it doesn't, you don't have to monitor the residuals per se. You just take small steps, and and you just do these two pressure correctors. But a couple of things to point out. If you see here at the start of each time step, it prints out the mean, like the average, and the max current numbers. So just to remind you, the current number of 1 means that the flow in this case is traveling one cell per time step. So the time steps are 5 milliseconds. So in 5 milliseconds, the max current number is 0.8. So it means that the furthest the fluid is traveling in any cell is 0.8 of the size of that cell. So for the piezo algorithm, it's typically only stable if the max current number is less than 1. So you can see this case has been set up to be as fast as possible, essentially, but still being stable. So if you double the current number in this case, uh, it may blow up the results. That may not make any sense. Okay, so that is run. So if I go ls in the directory, you'll notice a couple of things. We now have these directories called 0.1, 0.2, 0.3, 0.4, 0.5. So when OpenFOAM solvers run, they write the results to time directories. So if 0 was the starting time directory with initial conditions and boundary conditions, 0.1, 0.2, 0.3, they represent 0.1 seconds, 0.2 seconds. And if we ls, say 0.1, you can see it has a velocity file, a pressure file, and phi is a mesh flux, which we won't care about, and then there's some settings printed in uniform. But essentially all OpenFOAM is doing is, if I look at that velocity file, is it's actually just writing out the velocity vector for all 400 cells, 20 by 20 in this case. And then if I were to Control S to search down for the boundary field at the bottom, you can see it still has the boundary conditions here. It's just the internal field has changed. So this file is just like our 0 file. It's just instead of uniform 0, 0, for the internal field, it has actual non-zero values. If I go Control XF and open the P file, you can see here's the pressure results as well. So these are gauge pressure. So that's why they can be negative as well. So that's all it's doing. So if I go back to PowerView, um, which is here. I'll close this one and I'll go back to this one. So if I click refresh, and then with my time controls, if I click refresh and then click one of the time controls, then it'll pick up the new time steps. By default, it doesn't read 0, so you can often just turn this off just so you can actually see the 0 time as well. And now I'm going to color it by the velocity field in this case. So the velocity field is essentially 0 everywhere to start, but if I skip forward, and then if I click this rescale with a little eyeball, um, it should then rescale it, or let me try one of the other buttons if it's not working. Okay, I'll use this one instead. So if you rescale it, you can see this shows the velocity field, and you can see the pressure field as well. And for example, the velocity field, if I press play, I can see it changing, but it doesn't really change, say 0.5, 0.4, 0.3. And yeah, it doesn't really change much. So if I the first time that second changed a little bit, but it's basically reached its steady state. So they're the actual values written out by OpenFOAM, but it's often convenient to tick this box while you're on case.foam to click the create cell to point filter data. So PowerView will just interpolate the cell values to points, and you'll see now we have the point versions, and it's just for visualization. It can be kind of nicer to see the smooth values. Also, if I click this over here, I can set the number of contours here. So for example, like in PowerView or in Abacus, you might have just a finite number of contours. So if I set to 12, for example, and I might actually just save that as a default, then you can see these nice contours that you can play through. Okay, in terms of extracting kind of more information from the results, there's lots of visualization steps you can perform. So most of the common ones, which are called filters in PowerView, are along here, but you can find all of them on filters alphabetical. So this is all the different ways you can like post-process the data. So I'll just look at some of the most common ones. So for example, here is called a clip. So if I click clip, it lets me cut the geometry with a plane. So I can click apply, and you can see it's like that. I can drag this plane back and forth. I can drag its normal around, and I can click apply again. And then when I'm happy with it, I can just turn off the plane. And then there's lots of other settings as well. You can turn on crinkle clip, which just shows the actual cells that are cut, or you can invert it as well to look like that. So you can turn off the plane then, and you're happy with it. And you'll see that creates a new data set there that you can perform additional manipulations on. So I'll remove that one. There's also slice, which is just like clip, except it just keeps the slice itself. It doesn't keep all the geometry on one side. There's also iso contours. So for example, pressure, if I just want the iso contour at 0.24, I can press apply, and that's actually the surface that where the value of pressure is that. And so if I delete those and then maybe make a range of 10 values from min to max, generate those, or type them in manually and press apply, you can see that they're the iso contours of like the low and high pressures in the corners. In this case, if I turn on the little eyeball, if I click the eye just to the left of these, you can turn them on and off. So obviously I can't see the contours if the original one is turned on. So it can be nice in this case to change the opacity. So for any of these data sets, you just scroll down, you can normally find opacity here. And let's say if I set it to maybe 0.2 or something like that, maybe even lower, then it lets you see the both things at the same time. So that's nice. So while still clicking on case.foam, so whatever one I'm selecting here, that's what the filter will be applied to. Because say this contour is actually its own data set now. So you can look at mesh, it's actually like a surface mesh. So we don't want to apply filters to that one in this case. So another one we might do is on the original case.foam is if I use these glyphs. So I'll just go yes. And I'm going to pick the orientation to be the velocity and then the scale to be the velocity. And I will just drag this across a little bit. I'll click this auto rescale if it hasn't been selected, and I press apply. So that will create vectors, you can see, that are scaled by the local velocity direction and magnitude. So you can see it's all constant at the top. They're actually colored at the moment by pressure, so maybe I'll color them by velocity. So you can see that you have these nice contours. So you can start to see the flow field in this case. You can change, there's various settings you can change about like opacity, and if you click these cogs, you can get extra settings. Say like if you want to increase the resolution, you can see they're a bit blocky. Maybe if you want to set to more sides, just so it looks kind of smoother and things like that, you can do that. So I will hide that one, go back to case.foam, and then I'll look at streamlines, which is another popular one. So if I go streamlines and I'll turn on this here, so you can just see. So by default, it has to start the streamline somewhere. So by default, it just puts a line from one corner to the other corner. If I press apply, then it'll just seed streamlines along that point, and then it'll just figure out, follow the local velocity field. So it's making a lot of them here. So I probably want to use much less. So I go down to this resolution, maybe like 20 is more than enough. Okay, so that's fine, 20. And then I'll just turn off this show line. As you can see, I have the 20 streamlines. And maybe my original case.foam, I'll change the color to solid. And the stream tracers are colored by pressure at the moment, but I could color them by velocity. So they're a bit thin at the moment, so you can change the thickness of the lines. Somewhere it'll have line thickness here. If you click the cog thing, say this line width here. So you can set that to say 4 and just makes them thicker. But you can also render them as tubes, and that will make them thicker. But you can, let me see if I go 4 there. Yeah, very good. So maybe even 10. So if you render them as tubes, it can make them look nicer and easier to see. But you can actually do that same thing if I turn that off. And while clicking on Extreme Tracers, if I go Filters, Search, and then Tube, that makes a tube filter, and it does the same thing, but it just gives me more control over the scaling and the resolution. So if I click apply on that, then I have, okay, they're bigger in this case, but I can say decrease how large they are. But you can also say, if you zoom in, you can see they're a little bit kind of bumpy. So instead of having 6 sides, I can set it to maybe like 20 sides. And I press apply, and then they're a little bit smoother. Very good. So there's other things you can play with. In Power BI, it's mostly intuitive. But if I go back here, if I wanted, I could rerun this case. So if I go 0U, maybe I wanted to increase the velocity or increase the viscosity. I can just change that number, save the file. But notice I have results now, so I need to delete the results. So I can just go remove 0.1, and that would delete the first one, but I'd have to do it for all of them. I can use wildcards to do that, but OpenFOAM does have a built-in command. Foam list times will show you all the time directories in the current case. But if you go foam list times -rm, it will just remove all of them. So then I can rerun the case again, and they're back, and I can press up to go back and find that again and rerun it. Okay, so this is the end of this tutorial.